Hello everyone. In this video we'll be looking at quantifier negation. It's our PD plus rule. It works just like the SD plus rules of replacement in that you can perform this inference rule on part of a line. And also, as indicated by the two arrows here, they look a little different than the ones in the book. You can move back and forth. Each of these sides is input for the other side as output. You can take the left side as input and get the right side as output, or take the right side as input to get the left side as output. There are two formulations of the rule, but the syntactic manipulations are basically the same. Basically, if we move from left to right, you can take a negation sign that's on the outside of a quantifier, drag it across the quantifier, and then change the quantifier from universal to existential. Or, if you're dragging the negation sign across an existential quantifier, then you would turn it into a universal. And as I said earlier, you can also move from right to left. Let's take a look at how this inference rule will work in some relatively simple derivations. So when we were doing translation problems in predicate logic, we looked at two different ways of expressing the statement, some f's are not g's. So let's take a look at that. Some f's are not g's. There is an x is f, and it's not the case that x is g. Some f's are not g's. We noted then that this is logically equivalent to saying not all f's are g's. So the negation of for all x, if x is f, then x is g. But what we said then was that these two statements are logically equivalent. We actually couldn't prove that they're equivalent using our semantic methods, but now that we have derivations, we can prove that they're equivalent. And this is actually a nice problem to show how quantifier negation works. We're going to use quantifier negation right alongside some of the other SD plus rules. So this would be a good refresher for some of those rules we saw several weeks back. So let's set up a derivation. We're going to derive the negation of the universal, negation of for all x. If x is f, then x is g. And we're going to derive it from the existential. There's an x is f, and x is not g. That will be our primary assumption. It'll be our only primary assumption. So figured out how to make straighter scope lines. This should be plenty of room. So here's how we're going to do this. Give me just 1 second. What we're going to do is we're going to perform a series of SD plus rules to our primary assumption. Again, these can be performed on part of a line. So let's take a look at this. Suppose I work in 2 tildes in front of that fx. That's line 1, double negation. Double negation says you can add 2 tildes to a component, or you can take 2 tildes off if you already have them. So in that case, we can look at the expression between the parentheses, the open formula here, double negation fx ampersand negation gx. And what we have there is actually input for the rule De Morgan's, again, performed on part of the line. You can think of it this way. It's a little dangerous to do this. You can think of it this way. You're factoring out the negations that attach to those two conjuncts. And I made a mistake. Let me fix this real quick. When you factor them out, then you have to change the ampersand to a wedge. So that's line 2. De Morgan's. The next thing we're going to do is we're going to look at this, again, this quantified expression here again between the parentheses, and we see that we have the negation of fx, wedge gx. That's input for implication. So we're not going to change anything outside the parentheses. We keep all that the same. To apply implication, we change that wedge to a horseshoe, and we drop the tilde off of the left disjunct. So we just get fx there. That's line 3, implication. And then the moment we've all been waiting for. Let's take this tilde on line 4. We're going to drag it to the left across our existential quantifier. And when we do that, we've got to change that existential to a universal. That's line 4, quantifier negation. And that's our target sentence. So we just derived not all f's are g's from the single primary assumption, some f's are not g's. That's actually half of the equivalence proof. To prove two statements are equivalent, we have to have two proofs. The first one, we derive one statement from the other, and in the second proof, we prove the other from the one. So I'll leave that part of the problem for you to do. How would you derive there is an x, fx, and not gx from this statement? Not all f's are g's. We also talked about two different ways of expressing the statement no f's are g's. So one of those ways was to say for all x, if x is f, then x is not g. We also said you could translate that as the negation of an existential. We said that these are logically equivalent statements. The top one could be read, all f's are non-g's, and the bottom one could be read as saying, not even one f is g. There's nothing that's both f and g. So these were logically equivalent expressions, or so I claimed. And now we can prove them, and it's kind of nice to be able to use quantifier negation once again to prove this equivalence. So let's start with our target sentence. Let's say that we're going to derive, we could derive either from the other, but let's derive the negation of the existential from the universal. For all x, if x is f, then x isn't g. And that will be our primary assumption. Let me try once again to draw my scope lines here. That's in a good spot. Okay, so once again, we're going to apply some SD plus rules. So inside the parentheses, we have a conditional. Let's apply implication to it. And let me slow down just a little bit here and show you what we mean. Let's apply implication to line 1. Implication inside of here means we're going to keep the tilde g, x is the same. We're going to change that horseshoe to a wedge. Then we're going to add a tilde to the antecedent, not fx. That's implication on line 1. Now, if you look at line 2, you see that it's a disjunction of negations. You might think that it is input for De Morgan's, and in fact it is. So to do that, we take a negation sign and give it full scope, fx ampersand gx. So all we've done is we've changed that wedge to an ampersand. We took these two negation signs, basically kind of factored them out, moved them out to the left. That's line 2, De Morgan's. And then on line 4, what do we have? We have a quantifier and a negation sign side by side. When you see that, you know that you can apply quantifier negation. This time we're going to take that negation sign that's to the right of the quantifier, and we're going to drag it across to the left, and then we're going to change the universal to an existential quantifier. And the upshot is our target sentence, the negation of that existential generalization. It comes from line 3, quantifier negation. Once again, we've only done one of the two proofs necessary to prove that those two statements are equivalent. I'll leave you the exercise of proving it the other way. By the way, those two proofs that I didn't work, they can be done pretty quickly. All you have to do is work the second proofs backwards. So your first move would be quantifier negation, then De Morgan's, then implication, and then you're going to be home free. So that's a quick little introduction to our fifth predicate derivation rule, our PD plus rule, quantifier negation, and an illustration of how useful it can be when you combine it with other SD rules, SD plus rules especially.